Well, thanks for joining me today, everybody. I wanted to spend a bit of time with myself and Blake here going over a new connector we have that is intended to make the whole process of virtual commissioning sort of easier and more effective than ever. And I'll start just by talking a bit about the motivation here. A lot of you might be familiar in your industries with the relative cost of design changes as you move along in the development of a certain kind of product. If you catch something that you need to fix earlier in the design cycle, it's typically a lot cheaper. And those numbers are going to vary really wildly depending on the industry that you're in. But once you get along all the way until a release to market, these last few stages end up being extremely costly. And we kind of break the issues here into two different categories, the way that we look at it with our software. On the right here, these are typically issues that you would find, we say, without digital twin based techniques. And what we mean by that is just simply when you build a physical prototype, or when you're commissioning a machine and you're really trying to bring your PLC together with the machine and get it set up. Once you've got the hardware in your hands, you'll find issues sort of in this side of the chart. And on the left here, these are the issues that you'll find often with digital twin-based techniques. And that is just to say that when you're doing sort of integration testing, or you're trying to look at how your control code might function, or see what the system-wide interactions are between different areas that you're modeling, when you find issues in software and in the sort of virtual space, those issues appear early on, and as a result are much cheaper to fix and much quicker. And there's a bit of data for this. There's some research from a whole collection of NASA programs that were analyzed over a couple decades. And although it's harder to justify a sort of ROI and just throwing money on the front end of a design process, at least some numbers do show that even if you can iron out a couple kinks that you'd otherwise find closer to prototyping or even production, there's huge cost savings in that. So being a little more proactive, even just a little more on the front end of your design process, is going to end up saving you quite a bit down the road. Now, the term digital twin has been used in a variety of ways over recent years, and it's really becoming a more sort of common terminology. But there's still different types of these, and people interpret them differently. So I want to make a distinction here to first talk about a sort of plant level digital twin. And there are companies that sort of advocate for this kind. And this is more about the whole line itself. So this picture you're seeing here, this is about trying to have a digital twin to help work on the sequencing from machine to machine, or to look at timings across an entire line and what that might have to say about potential throughput. So this is really a sort of plant level of analysis here. But the digital twins that we're focused on here at MapleSoft are the machine level digital twins. And this is the virtual representation of all the dynamics and physics at play of what's going on in that single machine. So it's not the timings of how these 8 machines together are going to be passing parts between them, but it's really the forces and the loads experienced at different joints or different motors in your design. And this kind of digital twin, it can help give you answers to different kinds of questions in the plant level. So they do complement each other, but we're going to be speaking about this machine level digital twin. And especially we'll be speaking about it when it comes to this virtual commissioning phase, and how having a digital twin like this is sort of the foundation for using this new B&R MapleSim Connector. A quick sort of how it works here is, although you don't have to start with CAD, typically you're going to have some sort of CAD information for the project that you're working on. And you can just import that straight into MapleSim with an import tool that we have. From there, we're going to bring that model in, and once you split it apart into the sort of rigid subassemblies, all of the sort of mass and moments of inertia, all that data comes with it. And from there, your job is to sort of bring that model live and start to drag and drop different components in. That'll be motors, gears, joints, and start to actually model the dynamics of what it is that you're hoping to build. From that point on, you'll define a little bit of the motion path, and we've got some new applications that help you define motion for your products within our software a lot easier. And from there, you have the option then to perform all sorts of analysis on what the dynamics are going to be for a variety of subsystems within what you're building there. So that's a very high level, just quick view of what you would be doing to build a digital twin. And there's lots of details within that, but that's sort of a very general overview. And to say there's many details is definitely true. And for any of you who are looking to take this a bit more seriously, here at MapleSoft, we offer all sort of training and services to make sure that if this is something you're interested in, that we'll make sure it's a success, even if it's your first time working with tools like this. So really getting to the point of the webinar here, which is virtual commissioning and how this B&R MapleSim Connector has really made it a lot easier for folks who want to adopt this workflow. So you've got that MapleSim model, that digital twin that we just spoke about. And then we use the functional mockup interface standard, which is just a way of encapsulating the model as this executable item that you can sort of run tests off, and you can interact with it in a variety of ways. So now with this connector, we're going to package it up as an FMU, and we have all the applications for that. And then this FMU now can be taken into B&R Automation Studio and interacted with in a variety of ways. You'll be able to actually visually see the three-dimensional model moving around. You can pass parameters back and forth so that you can actually adjust parts of your model from within B&R Automation Studio. There's a variety of ways that you can now use it in Automation Studio when you're doing your controls testing. So all that was what I just had mentioned. An example being, say, you can test fault scenarios by adjusting frictions on a certain component. But a whole bunch of opportunities become available to you by just now bringing that FMU into Automation Studio. So just a quick highlight of benefits before we get into the software itself, and you can see what this workflow looks like, how simple it's become. From the MapleSim side of things, just by having a digital twin allows you to perform analysis and iterations on the concept work that you're doing on your machines way faster than you otherwise could. You might want to optimize for sort of minimizing load at a certain place in your design, or maybe you want to maximize throughput of how fast this thing can move before the components you're using aren't going to be sufficient. You can run those kinds of analyses very quickly with a digital twin from us. And that's going to have a lot of value in sort of speeding yourself along to further stages in your development. From the virtual commissioning side, there's a variety of efficiency benefits here in that you can do a whole variety of controls testing that's going to reduce the amount of headaches you'll encounter when you're physically commissioning this thing. And many of you could probably relate to the reality of how much of a headache that is when you're trying to bring your controls together with the machine itself. And there always seems to be something that's going to go wrong. But if you can cut out half of those errors, that's going to save you a ton of time. And from the safety side of things, you can test certain situations that in real physical reality would break the machine, where now you're going to have an option to test a variety of different fault scenarios that would otherwise potentially be unsafe to test. So you can do a bit of sort of robustness testing within Automation Studio and have it based on a really accurate model of the machine that you're going to be building. And you'd probably want to care about this depending on a huge range of where you might be in your company. So from somebody just being a designer, of course, having some more evidence-based design decisions and seeing the impact of some of your potential design choices, that's going to help you out quite a bit. And then from a managerial perspective, anything that's going to help with your cost margins is going to be a huge bonus. Even just having more justification to prevent oversizing motors just out of a sort of abundance of caution. You can have a lot more data to tighten those margins up. And then it goes on to operators are going to enjoy being able to understand the sort of operating limitations of their machine. And even someone as far away in the company as the sales staff, they might be able to now understand the limits of the machine performance with, say, they've got a custom order coming in and they need to know if the machine's going to be able to handle this particular potential working environment. A salesperson could be able to use just a quick designed application that MapleSim can make that could just walk them through a workflow for a potential customer if the machine would fit their needs. So there's a variety of ways these things plug in, and they all work a little bit faster than having to wait until you've got this machine sitting there. With that being said, with all the preamble we've done here, let's get right into the software. And I'm going to pass this over to Blake. Blake's an applications engineer here, and he's going to take you through what this actually looks like in the software.
Awesome. Thanks, Graham. So I'm just going to open up a fresh session of MapleSim. For anyone who might be new to MapleSim, what we have here is on the left a list of libraries that we have. This is where the various components that we have accessible to us live, and we can use to create our model, which is going to go in our canvas here in the middle. And as we add components, we will have properties that we can adjust on the right. So for example, for this rigid body, I could change the mass, the inertia, and different initial conditions. So I'm just going to really walk through the workflow that Graham was explaining. So going from importing CAD all the way to bringing this FMU into Automation Studio. So I'm just going to go into our import CAD option. And from my desktop, I'm going to grab this slider crank step file. We do support a host of various CAD files. So typically, whatever software you might be using to create your CAD, we will support. So bring in my file, and it's going to open up the import CAD window, which is going to show that 3D visualization. So let me just rotate this for us a little bit so that it's upright. There we go. So this is the CAD that would have been designed in, say, SolidWorks, for example. I've already gone through the effort of kind of grouping different components into parts. So I can see if I select my crank, if I actually change the visibility so that I hide everything else, I've made this my crank. So I've selected the different components to create this part based on things that are essentially lumped together, or as this crank rotates, all of these are going to be part of that dynamic. So I will bring everything back to show everything. We do have a lot of other webinars that talk about importing CAD and kind of some of the details, so I won't go and build the full CAD, but I will just give a bit of an idea of what really goes into creating this and bringing it into MapleSim. So we have this coord option, so we select it, and this allows us to define different coordinates that we might be interested in our model. So in this case, I know that I want to place a chord here because I'm going to have rotation about this axis, and I see that it's been added to this shaft. I'll give it a name that is a bit shorter, so I'll just call it A, just for the sake of this demo. And what I can do is I want to be able to connect this crank shaft to my base. So I will actually copy this by Control-C. I will then go to my frame, select the base, and I'll paste it with Control-V. And so this is going to give me essentially a connection location on my crank component as well as on my base component, where I can then define this rotational motion. I will also add one on my base. This is going to help me fix my base to the ground. So I'm going to change the name first. I'll change it to ground so I know that this is the one I want to connect to the ground. I can change the properties. In this case, I actually want to place it at the center, the bottom of this base. So when I zoom out and rotate this, we could see that I've placed this ground location just at the bottom and at the center. So ideally, I would go through and I would want to add these coordinates at for all the different components and all the different parts that I have in my CAD. But just for the sake of time, I will just import it as is. I get a message telling me that it's been imported successfully, and it gets added to my local components. So these are components that are user generated versus the ones that are built in. And I see I can drag in my frame, I can drag in my crank. I'm going to show the port name so I can see what they're called. Just flip this component just so that it lines up a little bit better. So I see I have my ground port, so I want to fix this to the ground. I want to define a rigid connection. I'm going to go to our library under multi-body. under bodies and frames and pick my fixed frame. I just click and connect to tell it that I want to connect the ground to this fixed frame, which is just located at my origin. Between my crankshaft and my base, I want to have a rotational motion. So again, under multi-body, I'm going to go to Joints in Motion, select my revolute, which helps me define rotation about a single axis, and I'm going to connect these. Last thing I'm going to do is I'm just going to change the direction of gravity. For my CAD, I actually had Z up as my direction of gravity, so I change it so that gravity is along the Z axis. So without adding any other components, I can actually perform a simulation, and we're going to be able to, so we see it's generating the equations, it's preparing it for integration, it's going through and solving it, and then my results are going to pop up. So we see in the results viewer in MapleSim, I can see my 3D CAD, I see the crank that I brought in, as well as the base, and if I hit play, I can actually see a simulation. So in this case, we see it swings back and forth, since it starts in this initial position, and then under the influence of gravity, it just oscillates back and forth. What I could do in MapleSim is I could actually go in here for my revolute. I can actually add some damping. So I can I'll add a small amount of damping. I'll run another simulation. And this is just to kind of give the flavor of what you can do in MapleSim and what are kind of some of the options that you can play with. So now that I've added damping, we expect that instead of just oscillating back and forth, it eventually comes and rests in this position. I can redo that. And you could play with different values for the damping. You can add other effects as well. And that's kind of one of the advantages of MapleSim. And what's nice about bringing in this CAD is we get that kind of nice rotational motion, and we're going to have the effective inertia, because when we bring in our CAD, if I actually take a peek inside this component, I have these CAD components that are going to give me that visualization, as well as this rigid body. So this rigid body is taking all the information that was in my CAD for that crank shaft. It calculates what's the total mass, as well as the effective inertia about that coordinate that I defined. So this is really why we recommend, and if you have CAD available, it's always nice to bring it in. Otherwise, you have to kind of figure out what would be your effective inertia, what would be your masses. But if you've done all this design in another software, you kind of get it for free when you bring it in. So now I'm going to do a little bit of a cooking show here and just go to another session where we have a completed model for the CAD. So we see in this model, we actually have ports defined for all the different components, and they're all connected. So if I run a simulation, now we're going to have the full CAD, the full slider crank. And I've also added this component, which is a speed driver. So I've attached it to that revolute that gave me my rotational motion between the base and the crank. And so I'm going to actually be giving it a constant speed of 5 radians per second. So now we see in our simulation, our slider crank is just rotating at this constant speed. Once I have a model set up like this, I can start asking it questions like, what is the angular velocity? What is the angular acceleration? What are the torques? I can also add more dynamics into the system. But for now, we're going to kind of set it up for one of our connector tools, which is actually the ServoSoft export. So I'm going to go in my 1D mechanical, my rotational, and I want to add some sensors. I'm going to be adding sensors to this revolute where my crank shaft is. So I'm going to go to my torque sensor. I can just drag it in. I'm going to rotate it just for the sake of kind of making it a bit of a cleaner canvas where I'm building my model. I'll add an angle sensor, and I will also add a rotational speed sensor. All right, so now I can add a probe to these so I can see the values. So I click this little crosshair, click here, I'll just call this torque, give it the units of Newton meters. I'll also add a probe here, just call it angle, radians, and I'll add a final one. And this will just be my angular velocity. This will be in radians per second. What's nice in MapleSim is when you add these probes, when you run the simulation and you see that 3D view, you'll also see graphs showing the results of these probes versus time. So this is kind of a nice, quick, easy way of seeing results very quickly. I'll make this big so that everyone can see. There we go. So now I can see as my simulation is running, I can see my angle is just increasing because my system is just rotating. My angular velocity is just 5 radians per second because I've enforced that. I've given that as a constant. And then I can see how my torque varies for this desired speed. With this information available to me, I can actually go into my apps and templates. I'm going to open up the B&R connector, and I'm going to go through this B&R ServoSoft data generation. I double click to open, and it's going to open up this app for me. I'm going to click load system. This is just telling the app that I want to connect to my current MapleSim model. So it's going to look at the model, bring in all the information, see what probes do I have available, so that I can help kind of set up the data that I want to export. So we can see that it's evaluating right now, so it's just trying to make that connection. So now I see I want rotational information for my position. I can just pick my angle, set it to radians, velocity, select that, radians per second, and for thrust I'm going to pick torque in Newton meters. I could specify the time that I want in step size. In this case I won't change it. I'm going to hit my preview export. So now what it's doing is it's running that simulation and it's getting me the results from my model for the angle, angular velocity, and torque that I defined. I can go through the various plots, kind of see the results. Here we see that the velocity is constant, so I just have a vertical line. And you can go through, these give you kind of like a nice, it's a quick view of some information that might be relevant, something maybe you want to change before you export this. And then all I need to do is I can just browse to my desktop, ask it to export. We see that it's just creating the Excel file. And if I actually just go here and double click, I see that I'm going to have data that's ready to be imported to ServoSoft. So anyone who's used ServoSoft for, say, motor sizing or trying to select a, kind of the appropriate motor that you might want to purchase for the system, this will look very familiar in this format. And this is ready to be imported as is. So I'll just go back to my model here. So that's one of our tools, but the other one that we want to highlight is the FMU Generation. So I want to set up this system so that it's ready to be exported as an FMU. So what I will actually do is I will just select everything. I'm going to create a subsystem. I'll call it slider crank. I'll go inside. And so what I'm doing now is I'm just defining my inputs and outputs. So I'll give this a name just so that it'll be a bit easier to find once I am in Automation Studio. So this is my angular velocity in. This is just my angle out. I have my angular velocity out, which will always should match my my angular velocity in, but we'll just put it so that we can see it in Automation Studio. And then I will connect, and I'll measure my torque. Perfect. So now I can go to my Automation Studio FMU Generation, double click, and once again from here, this is just helping me select which system or which subsystem I want to create an FMU of. So I will select my slider crank. I see it updates the display. This is the one that I want. I'm going to hit load. Again, now the app is making that connection, reading my model, getting the information, and it's going to help me kind of see what's available to me in terms of generating the FMU. So I can go through here. I see as my inputs I have 1, which is my angular velocity in. For my outputs, I have my angular velocity out, the angle, and the torque, the 3 ports that I define. For my parameters, I have this K sub D, which I've used to define some damping in the revolute joints. So I've added a bit of damping. And what I want to do is, I could leave this fixed, but then I wouldn't have access to it in Automation Studio. And maybe I want to be able to change it at some point as I'm running, testing my code or just trying to test some worst case scenarios. So I will change this to tunable. And then I'll go to export options. In this case, my default solver options are fine for me. However, I do have options, and I do have a fixed step as well as variable step. Advanced FMU settings for anyone who might need them or might know how to change these to really get the performance that they want. And by default, I do have this export geometric shapes and primitives. So this geometric shapes, that's going to give me the CAD that I've imported into the system. So of course, I want to see that in Automation Studio because that would be a great tool. Sometimes just being able to see your system running kind of gives you a bit of intuition as to, you know, if it's working well or underperforming, for example. So I'm just going to select my desktop again for my target directory for the FMU, and I'll just call this SC. I'll hit generate. So now what the app is doing is it's going through, it's taking all the information I've given to it, and it's actually getting all the source files that I need to create this FMU. So depending on the size of your model, this could be a bit quicker, a bit shorter. What it's doing behind the scenes is it's really creating some C code that can then be imported into Automation Studio. And in that process, we do try to optimize the code so that it does run as fast as possible. So I see that it's ready. So what I'll do is I'm just going to go, I see it's placed it on my desktop. Now what I want to do is I want to bring this into Automation Studio. So I actually have a virtual machine set up so that I can have access to Automation Studio. What I'm going to do first is I'm just going to bring over this FMU. So I can just drag and drop it onto my virtual machine. I'll make this full screen for us. So I already have Automation Studio open, and I'm just going to create a new project. So new project, again, I'll just call it SC for slider crank. I'm just going to keep the default option for the configuration. And for my hardware, I'm just going to pick a standard PC. So now Automation Studio is just going to set up that new project for me, getting everything ready. There we go. Always takes a little bit of time to get the new project set up. So now what I want to do is I want to add a library that's an FMU library. So I'll click here. Just filter some of the options for me. I'm just going to double click on FMU library. Seem to have just updated on me, that's fine. All right, so just click here again. There we go. Now I can select my FMU. So this is the one that I just brought in my temp folder. I don't need a sample program. I'll create one myself. I'll hit finish, and Automation Studio is going to bring in that FMU file. It's going to take all the source files, place them where it needs it, and it's also going to bring in the visualization for Scene Viewer. So you see that it's been added. I can actually expand this. This is the library it's brought in, and under this extra folder. So this is actually my scene. So it's not going to be anything exciting right now because it's not running. So let's set up a program. Let's actually get this running first, and then we'll go into Scene Viewer to see it in action. And just before I forget, I'm actually going to just update some of my system properties. This is just so that the communication between the FMU I generated and the system and how it's running are going to sync up nicely. So this time that I'm using is actually just the communication step size that I would have defined in the B&R FMU Generation tool from MapleSim, and this is the task class time. So with this set up, I'll save these configurations, close these tabs. Now what I want to do is I actually want to create a program so that I can execute this FMU and kind of see some results. So I'm just going to go here. I'm actually going to create a ladder program. So I double click, give this a more interesting name. So slider crank program. I expand it. I see it's already created some of these files for me in the ladder format. So I'm going to open up the cyclic. The cyclic is the one that's going to be running continuously versus the initial and the exit. So once I'm here, and also the same kind of flow and idea would work if you're creating this in, say, a C program or in structured text. what I want to do is I want to add, I want to insert a function. So I click this button, and I can search for my SC. So this is my slider crank. So you see that this is what was brought in from my FMU. So I click that, just give the name SC_0. And what I want to do is, actually I don't need these options here. Kind of clean it up a bit. I'm just going to add some space. I want to also add the visualization here. So again, I go to SC. I'll add the SC view. Now what I want to do, the only connection I really need to make is to connect the INST ref here. There we go. Again, I don't need this EN. And now what I want to do is in this program, I just want to set my my slider crank FMU. I just want it to be enabled, so I'll set that to true. My angular velocity in, I'll set this. Won't use 5 again, so we'll use 7.5. This KD, again, that was the damping. I won't set a fixed value just so then we can kind of show how you can update this in essentially real time and see how it affects the torque that you're going to get out. And then for the view, I also want to enable that. So I haven't defined yet these names, so it shows me as undefined. So I have to go to my variables and just kind of define them here. So using the same names from the program, what I can do is under the category, I can pick function blocks. Again, just search for the SC. And now I'm telling it that that variable is of type SC. And I'll do the same thing for the view. There we go. So I'll save that. Now if I go back to my ladder program, I see it's actually updated the type for me. So I'll also save my ladder diagram. And now what I can do is I can actually build this project. So I'm just going to do an offline installation. And so what it's going to do is it's going to take all the files, my program, it's actually going to, excuse me, it's going to compile everything and kind of do all the linking so that it can then run in Automation Studio. So it gives you some information of what's going on. We'll give you any warnings or errors. For those who are attending this, this might be a bit of a more familiar program than say MapleSim. So hopefully what you're seeing here and the way that it's built is quite familiar and just making a lot of sense. And you can kind of see that once I bring in this slider crank kind of FMU component, that you can really just, you can add control to it, you can design some logic, you can really take it as far as you normally would any other project. So I'll just create this local install folder. Close that. And now what I can do is I can open up a watch, and this is going to help me see what's going on with my program. So I'll add some variables. I'm interested in this SC knot. So I'll look at my angular velocity in and out, the angle out, torque out, and also this damping value. So we can see that it's going to run with this 7.5 radians per second angular velocity in. My damping is currently set to 0, and we can see our torque is quite small because there's no resistance. So what I can do is I can actually increase this, and we can see the value of the torque jumping up. And I can increase the damping further, make it quite high, and we see that the torque is increasing even further. So it's kind of a nice way to be able to change things kind of on the fly and see how it's going to affect your system. And again, you can add additional ports in your FMU, so any quantity that might be of interest, maybe it's some kind of position or multiple torques, multiple angular velocities. These are all things that you can have as data coming out of your FMU. And then finally, maybe we want to see this in action. So on our Scene Viewer file from our FMU folder, we double click, zoom in a little bit, try to get the lighting a bit better here. I will start the PVI. I'm in trial mode, so just give me this warning. And then we can see it in action. So we see we've gone from bringing in our CAD into MapleSim, creating a model that makes sense or is of interest to us, has the dynamics that we care about, generating an FMU, and then bringing it into Automation Studio, having some parameters that are tunable, having inputs and outputs, and also being able to see this 3D visualization. So at this point, I'm going to pass it back to Graham just to close up the webinar.
Thanks, Blake. Well, by now you folks have seen the whole process sort of start to finish. And I'm just going to end on one slide here, and then we'll open it up for questions for you folks. Maybe there's something you want to go a little bit deeper in. But just to say that you've seen this process now, and it's certainly easier than ever with the tools that we have. But for many folks that we interact with in industry, taking on some of these digital twin or virtual commissioning techniques is still new to a lot of people. It's still just a methodology that hasn't been fully adopted by many companies. So just to say that at MapleSoft, we recognize that, and we have a variety of services and training options that can range from as small as just a bit of training to get you started, or we can help be there with you side by side for an entire project and make sure that your process with working with this stuff will be successful. So just bear that in mind as you consider how these things can work better at your company.